So welcome back. This is the last one of this mini series. Don't forget that maybe let's have survivors photo at the donut break. Okay. Yeah. So let's give it to Boris.
Thank you. Thank you. Okay. So as promised, there is a third independent topic of the three, which we're doing in this summer school. So it will be slice rank. So this is basically the three techniques which we saw in this. We'll see the third one today. In this summer school, they're kind of quite different. So this is again a kind of different idea, and it's really cool. The birth of this idea actually goes to the rank arguments. Okay, we're not covering in these lectures. It's kind of, but it was also like Frankel-Wilson type arguments. So that she was inspired by this, but the current incarnation it actually looks somewhat different. Because we will be talking about ranks, but it won't be ranks of matrices. It will be ranks of more general objects, which is kind of cool. So before plunging that, let me tell you basically how this kind of got invented. What's the origin? So it started with the problem of Simonides theorem or Ross theorem. So there's a famous problem which is suppose I have a set A of 1 through n, and which has positive density, so which has at least epsilon times n elements. And here you should think epsilon is fixed and n is large, and the question was, does A contain some configurations and specifically arithmetic progressions? So, and this was first proven by Roth. So theorem Roth under this assumption, we show that A contains a return arithmetic progression if n is large enough. And this and again this is beautiful piece of mathematics. It's Fourier argument basically. Absence of free APs means so you have some kind of Fourier big coefficient, and then you basically pass to subprogression and integrate. This is again, I cannot do justice as much as I would like to, but to this, because it's not a topic of today's lecture, but this is beautiful piece of mathematics. Highly recommend to read it up. It's just fun. Okay, and then there is another super beautiful piece of mathematics. What Semereti improve this to that A contains not just free APs. It contains k-term progressions again if n is large enough. It's a function of epsilon and k. Yeah, his original proof was really again amazing. It's actually this is for this proof that he invented the regularity lemma. Even though again it was not quite fully explicit in the way you understand these days, and he also understood. It was a really cool proof. Nowadays there are much easier proofs available. Probably if you're a combinatorialist, there is probably relatively short proof going from density L to it, and this is probably the easiest for combinatorialists these days. Okay, but this is not what we're talking about, because there's a separate story about the bounds, how big this ends into be, and without going too long into this, it's let me say that the bounds are not great. So for example, for the 3AP, so there is again a construction which again we are not showing in this lecture. it's again, if you haven't seen, highly recommend to check by parent of a set A, slide one friend, without free APs and whose size is bigger than n to the 1 minus epsilon for every epsilon. Okay, now as is common in mathematics in general, whenever you try to solve problems involving integers or Euclidean spaces, it's a sensible thing to do to see what happens when you reduce the problem modular prime. So you're working in the finite field. So it's okay. I think in all the instances I know, maybe I'm just missing something. You're always going to get some easier problem which shares some kind of similarity with the original one. So it is definitely worth solving that, and maybe solve the maybe it will help solve original problem. So reduction might be it's a great thing. So because of those reasons, people looked at analogous problem in FP. So here's what this is what we're going to talk about. So we are going to look at now subset A. Let's say FQ doesn't matter too much. FQ to then, and it's A does not contain, okay, for us no free API. No free term arithmetic progression. It turns out that, for example, the argument of Roth becomes much easier and cleaner in this setting, simply because Fourier analysis is nicer on this. So if you so this is kind of nicer. So it's Mishulam basically first we proved the version of Roth's here, and it's basically a really simple argument. Okay. And the bounds, but the bounds we were getting for the Fourier analysis arguments were of the kind basically q to the n divided by some constant terms. And that's basically the type of bounds they were getting. So really what you should be thinking is that the size of our set is q to the n. And so this is really n divided by log n. And this is the type of bounds one gets from Fourier. And it's really hard to improve on them. Okay. Finally, Bateman and Katz did improve this by increasing the logarithm power of logarithm a little bit, but again, it was quite a proof. Okay, and they actually got very unfortunate. It was very unfortunate for them because very shortly after they did this improvement, the slice rank argument came about, and this is what I'm going to show, which is a lot to prove an exponential. Okay, so what we will show is the following. So A will be a subset of F q to the n. A contains no free term progression. Then the size of A will be less than some constant depending on q, won't be to the n, where the constant will be strictly less. So it actually it's an exponentially better bound. Just like power saving. So know that such a bound cannot happen in the integer setting because again there is this question. Okay. And the key to such an argument is what's called a slice rank, or which is a generalization of a rank of matrices to what's called tensors, which is a fancy name. Okay, so first of all, let's recall about matrix rank. So rank of an matrix M is the one way to define it. It's the smallest number k such that M can be written as a sum of k rank 1 matrices. And what is a rank 1 matrix? Well, here where rank 1 matrix whose ij entry is of the form some ai times each. So I wrote it slightly differently than we normally write. Normally we would write basically just product of a column vector with a row vector. But if you think about what it means, this means exactly this. The ij entry is the product of the ith entry of the column vector and the jth entry of the row vector. So this is exactly that condition. Okay. So the slice rank is instead of matrices. So matrices are rectangular arrays of numbers, and we will be looking at what's called tensors, which are higher dimensional arrays of numbers. So for purpose of this lecture, I will basically do all the calculations for just 3-dimensional tensors. So basically just matches are 2-dimensional tensors and just basically look at 3-dimensional one. And I'll say a few words something generalized, but again, it won't be really difficult. Okay, so let's define a 3-dimensional tensor with entries in some field F is just formally speaking is just a function so M, got the matrix here, from okay, so right, so you're going to use X as our index set. So normally for matrices we use numbers 1 through n, but again, we don't have to. Sometimes I will have matrices indexed with some other object. So we will just use some set X, which could be 1 through n if you want to index rows, columns, and the whatever I think you want to call it, the depth for the depth coordinate. Okay, so this is that, and the slice rank such a thing is the smallest number k such that M can be written as the sum of tensors of slice rank 1. Mi is slice rank 1. Okay, and what's a slice rank 1? Okay, so it's a one which you can factor much in a separate coordinates, much like this example here. It's of the form ax b y z, or you can factor. There are three possible ways you can factor things. So it can be factored either this or let's call it say c. C or B, C, F. Yeah. So just to make sure we're on the same page, I don't mean that it can be factored in each of the three ways at the same time. No. I'm saying it can be factored either this way or this way or this one, and all so and either way it will be give me what's called rank 1 tensor. When the rank is a slice rank. There is also something called, for example, tensor rank, which is an older notion where you're factoring all three coordinates, so it's ax, by, and cz. We're not going to use it. It's not going to be helpful to us, so I'm not writing it out. Okay. Yes.
Do you mean that for every such tensor, it is one of these three forms?
Yes.
So it doesn't have to be the same.
Correct. So in other words, yes, good point. So in other words, what we're saying that my m of x, y, z is over the form. It's a sum where we have some terms of the form b, I, y, z. We have some terms of the form c, I, y, d, I, x, z, and we also have some terms of the form e, I, d, f, I, x. Okay. And there are so here say I C where A plus B plus C is at most. So I guess strictly speaking, I'm defining. Yeah, okay, this is smallest game. This is smallest actually. So X is the same set. X, so this capital X. So capital X here. It's index set. Index set, which will always be finite. So finite index set. I mean, if you want to think of it as numbers 1 for n, like relations of n by n matrices, just think of the numbers 1 for n. But yeah, it will be just more helpful to this. Imagine we're doing these better objects. So. Okay, that's a definition. And the main lemma, which we all, basically everybody uses, is that the diagonal tensors have full rank, which is again, it's basically saying diagonal matrices have full rank, which is unsurprising. So let me just sort the lemma. This is basically okay. So let m x y to be defined to be some constant x x equals y z, maybe not a. Let's go d diagonal element. 0 otherwise. Then the slice rank of M is going to be equal to the number of non-zero elements among these. So it's like diagonal matrix. You got diagonal matrix, its rank is going to be the number of non-zero entries on the diagonal. Okay, so on the one hand, so in order to show its equality, we need to show two things. Then it can be written as the sum of that many rank 1 tensors, and then more difficult part that it cannot be written as a sum of fewer than that many rank 1. Okay. So first, the easy direction. No, if I basically take if I take the delta function, so basically, I'm looking. If I look at the just say, yeah, note that tensor. So let's go dx, which is just some constant. If x is equal to I j k, y j z k, 0 otherwise. So because this is the tensor where it just has a single non-zero entry, and this is non-zero entry is position I j k. So this tensor has slice rank 1. Well, that's easy. We can just basically write it as Dij y as ax byz, where x is going to be 1 if the x coordinate is what it's supposed to be, and 0 if x is not that, and then b y z is c if y z is equal to jk is 0. Okay, so this is easy. And of course, and if I'm taking this kind of tensors, and I have some tensor with a say L non-zero entries, so well, a sum of L such tensors, I can write a tensor there. So upper bound is easier because I can just basically do it one entry at a time. Yes.
In the definition, A and B has a condition.
No, it's arbitrary functions.
Every function.
Yeah,
Okay.
yeah, but it's like much like the ranks of matrices, right? This is just arbitrary vectors, arbitrary functions from the index set like 1 through n to the scalars. Okay, so this is upper bound. Okay, so let me just write it. And the slice rank of that particular tensor is at most number of non-zero entries for any tensor. Okay, lower bound for this lemma. So before proving the lower bound for the lemma, I will need an auxiliary lemma. So position that we will need. So let's say position. A sublime, I feel like. So if I have a vector space, so let's say U is a subspace of f to the n, then U contains a vector with at least dimension of U non-zero entries. Do this. So let's say let's say V in U is a vector with the largest number of non-zero entries. Vector with the largest number of non-zero. Again, by just renaming the coordinates, I can assume these are the first few entries. So by using coordinates, we might assume without loss in generality that it's the V1, V2, Vk non-zero, and but the rest of the coordinates then let's consider the intersection of this vector space U with the coordinate subspace in which the first k coordinates is zero. So I'm intersecting this vector subspace with this vector subspace. Well, okay. Well, this thing, each time I'm intersecting U with some new subspace, new equation, adding new equation to it. Dimension might drop by 1. So the dimension of this is at least the dimension of U minus the number of constraints I added, minus k. So this is just a linear. Now, if my assertion is false, so if the vector with the largest number of non-zero entries has fewer than dimension of U many entries, but k is less than dimension of U, so I think I need to go there. So in that case, that number is bigger than. Okay. That's the dimension of U. Then that intersection is at least one dimensional, and so there exists some vector W in U such that the first k coordinates are 0, but it's non-zero vector. Right, it's a vector inside this subspace, and I'm just going to add it to my vector. Okay, so then number of 0 coordinates in V plus W is going to be strictly more than K, because it's first K coordinates are the same as those in V, and we'll have some non-zero coordinates for that. And this contradicts minimality, and therefore the assumption that K was less than dimension of U is false. So we actually do have a vector with at least K non-zero. Okay, this is our sublemma. Now let's prove that lemma of what they are not tensors. Proof on the lower bound. So as a first of all, I can assume that all of my diagonal edges are non-zero. This is the only case I really need to treat, because I can just restrict my coordinates to those where it's non-zero. Okay, and that's enough. It will still have a lower bound for call. So with our slope in generality, all the diagonal entries are non-zero, and I only need to prove that it's a lower bound of size of x. Okay, so let's now assume that we have a way of writing that further as that something. And so this is the sum. A x I know. Okay. Well, we may assume that say this is non-zero. Otherwise, we just rename the variables. Okay, so we're looking at the A's, and there's at least one term here. I'm going to now look at the span of the A's. This is just this. The span 1, 2, 8. In other words, I'm looking at all the possible linear combinations of just a second. Now, the complement of, so orthogonal complement of this is of dimension n minus k. So if because the okay, so let me just probably be saying this. I'm just saying, okay, I'm just this is so by dilemma, by sublemma, which we just proved, sublemma. There is a vector. There is f. There is an f in the complement, in the total complement, with at least this many non-zero entries. Okay, so I just write down what that means. So first, what does it mean for f to be in a orthogonal complement of this? Well, it means the inner product of f with any of this a's is 0. Okay. Well, let's write that out. So i.e., if I'm looking at the sum of f of x, a on x, the x over all. This is inner product between f and ai. This is 0. This is and the second condition means that f of x is non-zero for at least that many of the x's. So now I'm going to take this expression and I'm going to take inner product with f. So in other words, I'm looking at f of x m x y z, and this is the sum of x. Good. So let's evaluate it, what happens here. When I look at the first summand, so this is going to be x is x. I'm going to get f of x, x, and there is going to be some b I y z. Okay. This is the first summand. Now I can take this out of the sum, of course. It looks like this. So this thing is 0 by the orthogonality. This is the crucial step. And as to the other two sums, well, I'm going to get, sorry, nothing we call plus, apologies. Still two other sums, plus I will have from the second I'll have ci y plus the sum over x of f x di xz, and then I will have the similar expression which I'm getting just lazy to write down with this third sum. Okay. This thing here is just as a function of z, right? I don't know what the function is, but it's a function of that. So this sum is really of the form, take function of y times a function of z. And this sum, which I was lazy to write, will be also the same kind. I will have a function of z, and once I sum of over x and times f of x, again I'll get some function of y. So all in all, what I obtain is a certain sum of the following form. It's sum over b plus c terms of something, some function of y times some function of z. So altogether, this is what happened. Now, what about this? So this is we'll get the right hand side, and this will be obtained. What about the left hand side? Well, left hand side is really easy because m is diagonal, so I can just write down explicitly what this thing is. So let me move this up. That's it. So this sum of f of x m x y z over x. Well, this is going to be it's a function of y and z. It's going to be non-zero only if y and z are equal, because otherwise we're getting 0 there. So the non-zero term here is only y when y and z are equal. What's the term? Well, we're going to get a d of property d, which is d sub y, and we're going to get it multiplied by f of y, like this. That's what it is. So, in other words, this thing here is an n by n matrix. N by n matrix with, well, as many non-zero terms as f has. 0 terms as f has. Because these are non-zero, multiplying by these doesn't change whether you're 0 or not. And this might be 0, or some f or some x 0, but this is exactly why we chose our f to have many non-zero terms. This is basically this condition. Okay, so now basically we have a diagonal matrix, which is the sum of a bunch of rank 1 matrices. So this is just, okay, usual algebra. So by the definition, well, it's not definition because we're using the rank of diagonal matrices being something. So, so by linear algebra, okay, linear algebra. We are going to obtain that the number of non-zero terms in A. Well, this is the rank of this thing. Okay, let's go with that. Either, so we have some name, is going to be at most number of b plus c, which is of course to say that a plus c plus a is at least n. So it means original sum had at least and some n's, which is to say the slice rank of the tensor was at least. So this is the main lemma, which you proved. Let me maybe say a couple before applying this, which we'll do after the break. Before we start the break, I want to make a couple of comments how this generalizes. Hopefully, at this point it should be fairly clear. So generalize this to higher dimensions, one is looking at the functions in more variables. Again, I will just write 4 because writing in full generality just introduces lots of notation to keep track of all the indices, which is does nothing except increasing length of the papers we write, which is good for everybody, right? So for 4, we are looking at say functions in 4 variables, and then basically you are going to, for slice rank, the relevant rank 1 tensors are going to be when you factor out one of the coordinates. C, Y, T, X, Y, W, Z, W, sorry, etc. Yeah, so there are total 4 types of rank 1 tensors. And the proof is going to work exactly the same, right? We're going to look at the A's, we're going to find something in orthogonal complement, take in a product, repeat. There is a, I mean, it's really historical of Luca, probably. There is a variation of this copartition rank, which is because historical fluke accident was introduced later. But in addition to looking at this expression, you also add all other ways to factor this, other ways to separate variables. So you also include these things like this. And so we're going to get 6 plus 4 old ones types. So this will be slice rank. So, and the proof we saw works for this equally well. I mean, if you think through this, it's generalized fairly easy. Yes. Okay, we won't talk about it, but I just want to mention just so that you are aware of this. Okay, let's take a break, and after break we'll see how to use this, and there should be a photo. So please survive. Okay, well, welcome back, everyone. We have this lemma about slice rank of diagonal tensors, and let's now use that lemma to prove an upper bound in the size of the set without three-term arithmetic progression in the F cube to then. Okay. That set and I'll see the then. Okay. So we are going to use X be the free set. Free set. So this is some subset of FQ to the N. We're going to look at the following tensor, a natural tensor, if you might. Find the M X Y Z to be one if X plus Y is 2Z and 0 otherwise. Okay, let's observe some things about this tensor. First, this tensor is diagonal. It's a diagonal tensor, and this is exactly because of condition of not containing free APs. Because when is it equal to 1? Precisely when the X Z and Y form a free-term progression. So the Z is halfway between X and Y. So this is exactly the equation for free-term progression. Except there is also the solution where they are not distinct. So X, Y, and Z are all equal, in which case it's equal to 1. So this is with the diagonal entries, all diagonal entries are equal to 1. And this is by free AP frequency. This is because free AP free condition. Okay. On the other hand, we can write this tensor in the following seemingly crazy way. And let's get on the board because the way is M X Y Z also is equal to the product over all coordinates of 1 minus the xi plus yi minus 2 zi to the power q q minus 1 like this, and this is the okay. So let's stare at this expression. So this expression in parentheses, this is 0 if the ith coordinates of x, y, and z satisfy that relation on the board on the right, and it's non-zero if they don't. And if you take a 0 and you raise it to some power, of course, it's going to be 0. On the other hand, if you take 0 and a non-zero number in FQ and raise it to the power Q minus 1, you're always going to get Q minus 1. So you're going to get 1, please. Thank you. Thank you. Okay. Yes. The multiplicative group of a field is cyclic, and so it's order Q minus 1. So you bring it to the order of the group, you're going to get identity. Okay. So this expression here is 0 if a condition holds, 1 if not. So if a single one of these conditions fails to hold, then you're going to get 1 minus 1. It's whole. This is 0, and whole product is 0. And if all conditions hold, you're going to get product of a bunch of 1s, and this is 1. So this is literally the same way, same tensor, but written in this kind of really weird way. Okay. Wow. So why we did this? We did this because this is a polynomial, and we know lots of things about polynomials. In particular, as a polynomial, it's of degree. Well, there are n products. Each of them is of degree q minus 1. So this is of degree q minus 1 times n as a polynomial in x, y, and z. And this is polynomial of fairly low degree, as it turns out. So I will write this polynomial as a sum of bunch of monomials, C alpha beta gamma, X alpha beta Z gamma. I mean, I'm still using the multi-index notation for the exponentiation. So this X is a vector, Y is a vector, and so forth. And so this is at most Q minus 1. Yep, and C the sum coefficients. Now, if in each of the summands, either the the weight of alpha or the weight of beta or the weight of gamma is at most a third of this number. So I will split the sum according to which of the three is has small weight. So I will write it. Maybe I should you see the next word so I have enough space. We'll write this as the first. I'll look at those two shows. Alpha is at most a third of Q minus 1. And it's the alpha beta gamma X alpha. And what I will do, I will just lump the beta terms and gamma terms down here. Oh, sorry. Oops. What did I do? What did I do? You never saw that. No. So now it's a sum over beta and gamma. Gamma, and then there are the y to the beta is into the gamma. Okay, and then there's going to be similar summand where beta being small. Again, there is okay. Okay, I put the prime because there are some terms which I already have in the first sum. I don't want to include them second time, so this is going to be this C is going to be 0 if it's already in the side summand. So this is gamma, and then there is going to be a similar term, but when gamma is. Oh, sorry, I forgot the term here. Yep. This is going to be y to the. Sorry. 3. This is y to the beta. And then there is going to be similar thing where I have z to the gamma here. Right. Okay. So we just split it into 3 similar looking terms. And the point is that this expression here is a function of y and z only, whereas this is a function of x only. So we get it. So in other words, this expression over here is a tensor of a slice rank 1. It's a product of something in x and function of y. And of course, same is true for every other. So what's the conclusion? Conclusion is that the slice rank of the tensor M is upper bounded by simply number of summands here. So it's by so we are looking at the set of all the alpha, set of all the alpha, so that alpha is at most Q minus n, and the each entry of alpha should probably also say that alpha length is at most Q minus, right? Because so I'm using this additional information. So if I'm looking at the degree of x sub I, right, it appears only once in this big product, and its degree is Q minus. Yes, thank you. This cycle. Thank you. Oh, okay. So, yes, because this is one thing. 3 times $30 here. Let's go with this. I mean, there is a way to improve this free We're not going to do this one. Okay. So let's estimate that. First we begin by estimating this. No, this one, okay, so this goes here. Let's first estimate this and then discuss how we can get basically sharp bar. Okay. So this quantity here, let me call this quantity Z. Okay, so this number of such alphas. So Z is just equal to probability if I pick alpha 1, alpha n at random among the from 0 to q minus 1, the probability that the total sum and is small. And how small is this times total number of choices, which is Q2. But this is just reformulating this. But in this way, it should be probably easier to see that we can just get a non-trivial bound on this probability by just using Chernoff bound. Okay, so Chernoff tells us that this is at most q to the n. Right, the mean of this random variable is q minus 1 over 2 because it's uniform between 0 and q minus 1. So it's going to be it deviates from the expectation by q minus 1 over 6 to the n. Okay, we are squaring that, and then we are dividing by the 2 times 2 times n, like this, and so no, I'm not. I didn't. Yeah, it's not correct. My martingale has basically differences not bounded by 1; they're bounded by q. So I will be divided by q. Okay, so and this is an exponential savings over the. Okay, so this will be enough to finish the proof of exponential saving. I want to also say how you can actually estimate this probability to actually precisely, so actually you can get not some kind of crude bound here, but actually what's the right exponent in this bound. So let me maybe say a couple of words about that, because this is common technique. So the idea is the following. So we are going to count, we're counting z. So, and we're going to ask ourselves how many of the alphas are equal to 0, how many of them equal to 1, how many of them equal to 2, etc. So we are going to just write it as the sum over various choices. So I will call them. Let me just basically, and maybe not before writing the sum, let me just write the words and then we will write this. So say we have P0 times n of alphas are equal to 0, P1 times n equal to 1, etc., up to PQ minus 1 times n equal to Q minus 1. Then the total number of alphas is n. So the total sum of these p's is a fraction of pi is a fraction of alphas which are equal to I. Total number is 1. So this is, I'm thinking of this as essentially probability distribution. What's probability? If I pick a random alpha, its probability is equal to the I. This is pi. I don't know this. Yes. And I also have condition that the sum is at most that expression. So I also have that the P0, not P0, P1 plus 2P2 plus P3, etc. minus 1 EQ minus 1 is at most Q minus. So these are the conditions on my choices of P's. And if I give you a vector or given a vector of P's, there are, well, how many alphas? Well, it's the binomial coefficient. It's the there are n positions total, and I will need to choose partition to the sets of size P0n, P1n, etc., up to PQ minus 1n. So this is big multinomial coefficient. Wait to choose alpha. And we can estimate this multinomial coefficient using Stirling's formula. Which so this is equal to 2 to the power just the entropy of this probability distribution times n plus lower order terms, where the entropy is defined in the usual way. It's the sum of pi equal to 1 over. Okay, and so now, so then you can write z as the sum of things like this. So z is at most, well, first of all, how many ways I can choose these numbers? Well, it's going to be just a polynomial in n, right? It's going to be how many ways I can partition n into q numbers. It's at most n to the q, n plus q choose q times the maximum of all of these guys to this entropies n plus or the smaller terms. And so you already probably is basically optimizing this entropy. And this is, you can do, for example, with using Lagrange multipliers if you have no better idea. And it is definitely a good way. And you can go and get a number. I mean, this is not a course on Lagrange multipliers, so I'm going to skip it. But this is how you estimate this kind of thing. Okay. Let me maybe quickly give another application of size rank method, which is kind of going to be very similar to the one we just saw, but it's just, to reinforce the method. And then we will finish. So it's about sunflowers. So what's a sunflower? Family, say A1, A2, ADK of sets is sunflower. Well, if when you draw a Venn diagram, it looks like this. So this is my first set. This is my second set. This is my third set. Okay, and set. Okay, let me just. Okay, I'm not good at drawing, so 3 sets is good enough. Okay, so condition is that AI intersect AJ is same for all pairs IJ. So every 2 sets intersect in exactly the same set. I mean, so when you draw it, it looks like some kind of a flower. I'm not sure why it's called sunflower, because sunflowers look different. But okay, that's not question to the inventors. So this is called petals. This is a stem. Okay, so the and there is a problem, which is still basically open. How large a family we need to guarantee a given size sunflower? Okay, so there are 2 versions: the without restriction on the ground set, but we'll talk about one, which is more famous one. We'll talk about the less known one, where you restrict the ground set. So suppose a family of subsets of an element set, and F contains no sunflower with K petals. How large and B? That's the question. Basically open, but it's, for the case K goes to 3, there's 3 petals. The slice rank gives a non-trivial bound. So this is what we're going to see. So we're going to see that if K is 3, then the size of a family F as above is going to be sub-exponential. That means there was exponential saving of that. Okay, good. So I'm going to identify sets yeah, right, with their characteristic functions, with their characteristic vectors, I suppose, vectors, i.e. elements 0, 1, 2. And again, X is going to be well, F, so it's F. So well, use X to be F. So we're going to define a tensor on say X, I might have an F. So this is going to be indexed. And what's my tensor? It's going to be MX Y. Very similar. 2 minus xi plus 1 I can't believe this is correct. Since it's late, I don't want to make mistakes in the middle. Let me double check. Sure. And this is fine. Yeah, so this is my tensor. Okay, so let's now see its properties. So first of all, for the diagonal, so m x x x. Well, I'm going to be so x's are all going to be 0, 1s, depending whether the element is in the set or it's not in the set. So this is going to be each cement is 2 or -1, and so the product is going to be non-zero. So this is non-zero for all sets in my family. Okay. What about the off-diagonal terms? Well, let's to me, I find it easier to if I draw a Venn diagram of arbitrary sets. So no, this is horrible. Sorry, what am I doing? Okay, that's better. A Venn diagram of 3 sets. Okay, so it's going to be 0. So m x y z is 0 if this sum is equal to 2 at least once. So there exists an element which is containing exactly 2 out of 3 sets. Okay, so it's 0 if we are, for example, in this region. So this is in 2 out of 3 sets. It's also going to be 0 if it's in this 2 out of 3 sets. Oh, sorry. Yeah, correct. Sorry, thank you. Yes, so if it's in 2 out of these 3 sets, or in the 2 out of 3 sets here. So it's 0 if any shaded region is non-empty. Well, but if all the shaded regions are empty, that means this is a picture of a sunflower, right? Also, 0 if shaded are empty and 3 sets are distinct, right? Because this is the sunflower free condition. So the only thing which oh, sorry, I forgot one step here. Okay. Oh, now, okay. So it's all now those things we need to do. What happens if two sets are the same and the third is different? Okay. And so here, I'm really sorry, I should change. My X is not F. It's the those sets in F which have some fixed size. And so I'm just going to pick some size, which again we'll discuss in a second. So this is, and then we're just applying to slice. So all the sets are the same size. Okay, so now next what we need to do is what if 2 sets are the same size? And so if 2 sets are the same and the third one is different. Okay, so now okay, so if say we got 2 sets the same, so x, it's not it's x, y is equal to y, and z is another set.
If the statement says that k is equal to 3.
Oh, okay. I need a free letter, sorry. M. So just
So x is the function of m.
correct. So let's go, if you want to call it x, then. And so this is, I'm applying slice rank to this. So what I'm doing, what I'm doing here, I'm going to bound the size of x sub m. Okay, for every m, and I'm just going to add those bounds for all m. this is the plan. So the size of f will be at most the sum of size of x sub m when we sum it over m. This is the plan. So if two of them are the same and the third is different, well, that means there is an element I, there is an I in n that is in set x, but not in the set y. And this is because the sets of have the same size, because the sets have the same size, namely m. So it's a diff. Okay, so that means when you think about characteristic functions, xi is 1. Well, zi, oops, not in z, sorry, and not in z, sorry, xi in y equals z is different, sorry. And z is 0, and hence xi plus yi plus zi is 2. And so this whole thing is again 0. And so m x y z is equal to 0 in this case too. Right. And this is where I'm using my sets have the same size. Okay, so by the same argument which we sketched about the let me just write it again. This was here, there. So now my m. So my m is a diagonal. M is a diagonal tensor, and is a polynomial of degree n in x, y, and z. And so m we can write as the sum, alpha is at most for 3 to the alpha constants and the z, beta z gamma, and then plus 2 other terms of the similar kind. And again, since this n over 3 is smaller than n over 2, by the same argument, we're going to get exponential savings by comparing. And then we are going to get. All right, so that's another application which is fairly similar, but again, there are more quite by now. There are probably half a dozen various applications of slice-rag method, and some of them are certainly looking slightly different. But again, that's it for today, and hopefully you got some techniques which you can use and recognize when you need to use them, and then you can basically delve deeper into some of the subjects we covered. That's the hope of this article. Thank you for staying to the end. I really enjoyed it, and hopefully you paying too. Thank you.
Thank you.